A traditional way to draw a structure in organic chemistry is to draw a zigzag line representing the longest carbon chain. And you could also draw out the stereochemistry utilizing wedge or dash. If you envision yourself flying up to this location, to describe the molecule, you could draw it out as a hydroxide group coming out of the plane to your left and a hydrogen coming out of your plane to your right, and a methyl group coming down the plane to the top, and an ethyl group coming down the plane to the bottom. This kind of bow tie convention really focus on the chirality center. In fact, when you have a molecule contains more than one chirality center, utilizing Fischer projection is really convenient in describing what directly bound to the chirality center. To draw Fischer projection, you follow 3 very basic steps. Step 1, you're going to focus on the chirocarbon. Draw a cross to represent the chirocarbon. Step 2, you use horizontal line represents the bonds coming out of the plane of the page, and you use vertical line represents the bonds going back into the plane of the page. General rule of thumb, the carbon chain is often drawn along the vertical line, usually following the IUPAC numbering system from top to bottom. Show you an example. We're going to use the 2-butanol as an example again. So, in order to be able to envision the molecule, clearly this is a good orientation to watch the molecule, because by doing that, the head is lined up with this carbon number 1, and the feet is kind of lined up to the larger number if you use the IUPAC naming system of the main chain. So we could draw our Fischer projection as a cross, as step 1 suggested, and we're going to draw out the substituents that bond to your horizontal line. That'll be hydroxide and hydrogen, and the substituents bond to the vertical line. That'll be your methyl and ethyl groups. Okay, we're able to describe the stereochemistry of this 2-butanol utilizing a Fischer projection. You could also easily draw its mirror image. Since it is its mirror image, it must be a chirality, have the same chirality center, but it's this molecule's enantiomer. That being said, all you need to do is to swap 2 substituents. Keep your methyl and ethyl unchanged. Swap the hydrogen and hydroxide. You're able to draw its mirror image. You could also assign R or S on either of these Fischer projections. You're going to first identify the priorities of the groups. Hydroxide is definitely number 1, followed by ethyl, methyl, and hydrogen. You're going to see hydrogen on the horizontal line a lot when you draw the Fischer projection. Under that circumstances, when you draw a circle from your most priority to the second, followed by the third priority group, you will draw a circle that's counterclockwise. But keep in mind, under these circumstances, the hydrogen is coming out of the plane instead of going down the plane. That being said, for this counterclockwise circle really corresponds to an R stereochemistry. And you could also try to assign R or S for the enantiomer, and I bet you that the chirality center has an S designation.